Okay, good morning or good afternoon, wherever you are. Thank you for joining this SimScale demo and discussion session on rotating machinery. If you've got any questions as we're going through the presentation or the demo, please feel free to ask questions using the questions functionality in GoToWebinar. That should be down the bottom right-hand side of your screen. And we'll be very happy to answer any questions at the end of the session. Okay, so let's make a start. First of all, I'll introduce myself. Hi, I'm Steve Lenne. I'm an application engineering manager here at SimScale. But the star of the show today is going to be Anirudh. He's going to be presenting to you on our solution for rotating machinery and doing a demonstration. So Anirudh is a member of our application engineering team here at SimScale with a background in CFD and mechanical design in the automotive and aero industry, and he's got a master's in mechanical engineering from Carnegie Mellon University. So first of all, I'm going to give you a brief introduction to SimScale. So who are we? Well, we're a Munich-based company. We were founded in 2012, and we have a global presence. So there's millions of simulations being conducted with SimScale worldwide. And we're funded, so we're going to be here to stay. What do we do here at SimScale? Well, we created the world's first cloud-based engineering simulation platform. On this platform, you can do fluid dynamics, CFD, solid mechanics, FEA, and thermodynamic simulations. And all of this is done using a web browser. There's thousands of companies that trust SimScale for their simulations. On the screen here, you can see a select few of those brands that use SimScale. How do we help them? Well, we accelerate their design process by enabling them to simulate earlier and easily test the performance and optimize the durability of their products, while improving their design efficiency by keeping everything in a cloud-based simulation platform. How does this compare to traditional simulation? Well, with traditional simulation, there's typically high fixed costs, and that's associated to the specialist hardware and software that has to be installed and maintained locally. This hardware and software is built for specialists, so these specialists need extensive training and extensive experience to be able to get the most out of the software. And typically the computing time is measured in days or weeks, and it's difficult to parallelize processes because the hardware and the software is occupied during a simulation. So how does this compare to what we offer at SimScale? Well, with SimScale, there's no upfront investment. There's no installation or maintenance of hardware or software, and it's very easy to set up. All you need to do is go to our website, create an account, and you can start simulating. We enable seamless collaboration within your organization so that different people can work on the same simulation projects. And we have a world-class support system built into the software. So you can use the in-software chat to talk to one of our specialists about your simulation. Typically, computation time is measured in minutes rather than weeks. And because we leverage the capabilities of a high-performance cluster in the cloud, you can parallelize as many simulations as you like. Okay, so that's the introduction from me, and I'm going to hand you over to Anirudh now. Thanks.
Great, thank you for the introduction, Steve. So today I'm really excited to showcase some of SimScale's features and how you can use it to run your simulations for rotating machinery. So the plan is I'm going to show you a couple of slides just to set up the simulation, and then I'm going to do a live demonstration and jump into the SimScale platform, and then we'll come back and compare some results. So the example I have chosen for you today is of a Francis water turbine. But the principles and the setup process I show you is valid for any kind of rotating machinery. So this includes things like pumps, fans and blowers, compressors, propellers, other types of turbines, anything really with a rotational component on it. You can model it using the same strategies that I show you. Now, Francis water turbines are a good example because they account for a significant amount of the global hydropower output. So any gains or any improvements that we can make in the efficiency has a significant impact downstream. So our objective today is to look at the design of a Francis water turbine, characterize its performance, and identify areas where we can improve its efficiency. So this is the CAD or the Francis turbine that I have in question. It's pretty straightforward. We have an inlet here right at the top. The water or the flow goes in from here, goes around through the spiral casing and hits this first set of blades, or what we call guide vanes. So these guide the flow towards the runners or the moving blades. So these are the blades that actually rotate and generate the power. So you can think of these guide vanes as the stator and the runner as the rotor. So once the water moves through the runners, it comes down through the back, and this is known as a draft tube. So this is where the water exits out, and we try to minimize any losses and equalize the pressure with the design of this draft tube. A couple of notes on the simulation setup that I'm going to use. So right now I'm going to study one operating point. So I'm going to specify an inlet flow rate. At the outlet, I'm just going to specify zero static pressure since it exits to the atmosphere. And I'm also going to specify a rotation for the blades. So this is the simulation point that I'm going to show you the results for and how I set it up. A quick note on the physics as well. So this is going to be incompressible steady state flow, and it's fully turbulent. So all the turbulence is completely resolved by using a model. Right. So enough slides. Let's jump onto the platform and look at some results. So this is the SimScale platform. The first thing to notice straight away is the URL. So you can see that SimScale is completely cloud-based. I'm just using a simple Lenovo ThinkPad as my work laptop. I don't have any fancy hardware acceleration going on in the background. It's just a simple internet connection, and it works reasonably well. So up top, just to give you some idea about the user interface, we have some features here where you can share your project, copy some projects as well, copy an existing project as well. On the left, you have your geometries where you upload different designs. And this is a simulation tab where you control all your simulations from. So you can see that the screen real estate is mostly occupied by the Shine 3D viewer. And right now we are in a post-processing state. So I have shown you the setup of this turbine where we specified an inlet flow rate as well as a rotation. And now I'm going to take a look at the results. So this is really to showcase what kind of data, what kind of information you can extract from running a simulation like this. So the way we post-process is using a bunch of filters, and I have a few set up already. So the first thing I normally like to do with any design is set up a particle trace so that I can understand some of the large-scale flow features in my domain. So what I'm doing here, as the name suggests, is I'm following a particle as it moves through the inlet, goes around, goes through my runners or the turbine blades, comes down and exits through the draft tube. So this gives me a good qualitative understanding of the flow. I can clearly see that once the flow passes through my blades, I can kind of see the rotational component or the swirl that is imparted to the velocity and how it exits out of the draft tube. So this is a good sanity check and a good way to understand some of the larger flow features. So now that I've done that, I want to understand some numbers regarding the performance. So I want to see, based on the flow rate that I specified, what kind of pressure differential is there in this turbine. So what I can do is I can turn off this particle trace, and instead of coloring this part, this transparent gray color, I can change the coloring to velocity. So let me just make this opaque. And when I do that, what I can then do is I can select, say, an inlet face like this and turn on the bulk calculator. So what this does is it gives me some statistics on a face, and I'm going to make sure that the flow rate is correct. So now that I know the flow rate on this face, I want to know what kind of pressure differential is there across the system that is causing this kind of flow. So I can just go on to my legend here at the bottom, and instead of looking at velocity, I can change this to pressure. So you'll notice when I do that, instead of looking at the average velocity, I see the average pressure instead. So this is my pressure head. So if I'm comfortable in a different unit, I can just change this to PSI, and I can see that at my inlet, I have 273 PSI, which is the pressure differential across my system. So now that I've understood some of the big picture of my design, some of the numbers behind this, I want to dig a little bit deeper and actually understand what's going on inside. So let me change this back to velocity, and I want to investigate what is going on inside the blades. So what I can do is, in order to see what's going on inside the system, I can cut it in the middle using a plane. So this is what I have done here. And now instead of looking at pressure, I can just change this to velocity to try and understand the flow around my blades. So now I can start to zoom in and look at how the flow is behaving around my stators or these fixed set of blades. Immediately, I can see that, especially on these blades towards the right of my screen, I can identify a significant amount of flow separation and recirculation, as opposed to some of the blades here, you can see where the flow is attached. So this is something we can definitely improve with another design iteration, which I will show you later on. So I can very easily just play around with this plane that I've used to slice my domain. I can just slide it up or down to look at different parts of my domain. And now that I've understood the flow around my blades, I want to understand how it is around my draft tube and how my draft tube is performing. So I can do that very easily by just switching the normal. So I can look at my view cube at the bottom right here, change the normal for this plane to X normal, and that way it'll slice the turbine right through the middle. So again, now instead of velocity, I will switch this to pressure, and I can then get an idea of how my draft tube is actually performing. So I will change this back to Pascal since I'm comfortable in SI units. And if I change the limit of the legend, that'll sort of highlight the performance of the draft tube a little bit better. So instead of looking at the default minimum and maximum pressures, if I change the limit, I can increase the contrast in the critical area, which is the neck section of this draft tube. So straight away, I can see that around this bend, the pressure equalization isn't great, right? So I'm going from green to yellow pretty suddenly. Ideally, I want this transition to be as smooth as possible to minimize any losses. So I can study this a bit further by using my inspect point tool. I can click here and it'll give me the pressure value at the neck. And I can also click here and I can see that there is a significant pressure differential. So there is a lot of potential for improvement in this design. And I'm going to show you how that is possible. So now that I have a good understanding of how my design is performing, let me go back and show you how I actually set this up. So let's go to our top and let's start with the geometry. So you can see that I have a couple of designs here. So you can upload as many different CAD models as you want by clicking on the plus button here. And we work with most common CAD formats. A few are listed here, and there's even more here in this section. What you need is just the flow volume, and as you can see, I have a second body as well, which is just a cylindrical region around my blade. So on the right, I can see a breakup of my geometry, and these are the two parts that I need to create a simulation. So let's get started. If I hit create simulation, you'll notice that we have a bunch of different modules that you can use. So it's not just simple flow analysis or CFD that you can do. You can also incorporate heat transfer if that's important, and you can also do a structural analysis or even frequency and harmonic. So in this case, I'm going to do a simple flow analysis. So if I hit create simulation here, you'll notice that I get a new simulation called Incompressible 3 under my simulation tree. So I can very easily just change this to say design 3 or whatever I want to call this. Right now, I'll just call this Thursday demo. Now, the workflow is pretty straightforward when it comes to setting up a simulation. It's pretty much top to bottom, and you control everything using these branches of the tree. The idea is to get a green checkbox everywhere instead of a red circle. So if I go top to bottom, I can see that I have a couple of red circles, right? I need to assign some material properties, and I also need to assign some boundary conditions. So let's do that. By clicking on the plus, I open up a material library. This has a lot of existing materials which you can use. I'm just going to click water here. But the important thing to remember is that all these properties are editable. So I can just change the viscosity or density and basically enter the properties of any custom fluid or mixture. Now let's specify the inlets and outlets. So that is there under boundary conditions. For my inlet, it's just a flow rate. So what I'm going to do is, instead of specifying velocity components, I'm going to change this value to flow rate and change it to volumetric flow rate. So I'm going to set 16 meter cube per second, select my inlet and hit OK. Similarly, at the outlet, it's just going to be 0 static pressure. So I'm going to choose pressure outlet and hit OK. Now that I've defined my inlets and outlets, the last thing I need to do is define my rotation. So that is there under advanced concepts, rotating zones. So I will create an MRF rotating zone. So MRF stands for multiple reference frames. So what this means is there's 2 reference frames. One is just the existing CAD, or the first reference frame from the CAD that we have. And we're specifying a second reference frame using this cylinder. So what I'm going to do is select this, the cylinder that I have around my blades. And all I need to do is specify the axis of rotation. So in this case, it's going to be -1. And I need to make sure that the origin is aligned for this reference frame. So once I have that, because we've specified the origin and the axis of this reference frame, the solver knows the rotation at every point. So basically, you can combine the data for the angular velocity from this reference frame with our original, and that way you don't have to simulate any moving meshes or anything like that to account for the rotation. Right. So now that I have everything set up, I am pretty much good to go and start a new simulation run. So I can do that by clicking the plus button here, and you'll notice that when I do that, I get some estimates. So the software is telling me how much time it thinks the simulation is going to take and how many computational resources it's going to use up. So I can just hit start here, and you'll notice when I do that, I have a new simulation run now running in the background. So this run has been sent off to a virtual machine in the cloud, and I'm free to do whatever I want while this is happening. So I'll get an email when this is complete, and I can come back and post-process it. But while this is running in the background, I can keep pre-processing or post-process any other results. So what that means is I can do like a full-blown design study here and characterize the performance of my turbine at different operating points. So I don't have to wait for my first simulation to complete, or in other words, it doesn't run in serial, it actually runs in parallel. So what that means is I can study a different operating point, 12 meter cube per second, hit the plus button here and start another run and call it, say, 12 meter cube per second. So this way, there's no limit to the number of virtual machines that you can use. So you can do a full characterization of your turbine performance using this method. So now that we've studied how to look, we've looked at how to study the performance of this particular turbine. Let's look at what you need to do if you have a different design. So if you remember the first design, there were a couple of shortcomings, right? We had some flow separation around the stator blades. The design of the draft tube neck wasn't too great. So I have a second design here uploaded as well, where the angle of the stator blades is different. And you will notice that I have a longer neck for this draft tube, and the outlet shape is different. So if I want to study this design, I actually don't need to do the full setup again. What I can very easily do is just duplicate my existing simulation. So when I do that, I have everything saved. So I have all the boundary conditions, material properties, rotation saved. I can just switch out my geometry and run this new design. So the process is very straightforward, but if you do run into any trouble, it is very easy to reach out to support. So in the bottom right, we have in-product chat. So this is staffed full-time by our application engineers. So you can just send us a message and someone will get back to you pretty quickly. Now, the best part about this is with a professional license, all your projects are completely private. We, nor the cloud service this is hosted on, have any access to your data, but you can give us explicit access by clicking on this checkbox called Share Project with Support. So what that means is using the same URL, our support engineers can pull up your project on their machines, and they can look at exactly what you're looking at. So that makes the support instantaneous. You don't need to browse forums or file a support ticket, send over a bunch of data. You pretty much get immediate responses. So now that we've covered the setup process, the support as well, I want to quickly go back to the presentation and compare some results for these two designs. At this point, I want to quickly remind you guys to ask any questions you have at all. So if anything in the setup process wasn't clear, or if you have some more questions, please feel free to use the questions functionality right now. Okay, so let's go back and look at some results in the presentation. So right now I am comparing two designs. This is the first one that I showed you where I had seen more flow separation, and this is the second design with the different stator blades and the draft tube. So immediately I can see that on my first design where I saw a significant amount of flow separation, I've improved that significantly just by changing the angle of attack of the blades. And here I can see the flow separation is a lot lesser. So that way less energy of the water is being wasted in the form of this recirculation. Next, let's look at the performance of the draft tube. So this is where we're trying to, if you remember with the older design, trying to equalize the pressure, and we don't want to see any sudden pressure gradients. So what I've done with the second design is extend the neck, and here I can see that the transition from green to yellow is a lot smoother, and therefore my losses are going to be much lesser. Next, let's look at the flow in some more detail that is coming out of the outlet of the draft tube. So on the left is the first design which had a circular outlet, and I can see immediately that the swirl component of the velocity is a lot higher. So any velocity here that is swirling or recirculating equals wasted energy from the water, right? So on the right, we have a second design with a square draft tube and a longer neck that we were comparing, and I can see that that component of the velocity is a little bit lesser. So this is also helping me minimize any losses. So the next thing we want to study is the blade surfaces. So this is a pressure plot of the front and back of my turbine blades. So this pressure differential is actually used to calculate the torque that these blades produce. And then this is multiplied by the power to get multiplied by the RPM to get the power. And then the power is used to calculate the efficiency. So this is the process we use to characterize the efficiency performance of the turbine. So now, since we have the power and efficiency of these different operating points, let's look at some performance curves that we can generate. So on the left is a typical performance curve of efficiency versus flow rate. So if you recall, I studied my design at a couple of different operating points. So 16 meter cube per second, 12, and I've studied it with a few others. So this is just a comparison of the initial design and the modified design, which I had shown you. And you can see that there is a significant improvement in the efficiency, especially at lower flow rates. On the right is another typical example where we're plotting efficiency, but now this time, instead of flow rate, we are looking at different stator blade angles. So the first angle had a significant amount of flow separation. And as we increase the angle of attack, I can see that the flow separation reduced, and therefore my efficiency is going up. So this is what I would use to determine the design and the angle of those stator blades. So now that we've covered how you can set up a couple of designs and compare them, I want to open it up to any questions that you have. I'll be happy to answer those with Steve.
That's great. Thank you, Anirudh. Yeah, this is a reminder to ask any questions that you may have. You can use the questions functionality down the bottom right-hand side of your screen, and we'll start answering the questions that we've already got in. But please ask any further questions if you've got them as well. So one question that's come in, Anirudh, is there a way to process the data locally?
Sure, yeah. So I'd say it's pretty straightforward to do that. Ideally, all the data is stored on the cloud and there is no limit to it. So we find that most of our customers tend to keep all the data in the cloud. But if you do want some additional functionality and to store the results locally or even post-process them, you can do that. So let me show you how that's possible. So let's go to an existing simulation run that I have. This is the one I showed you the results for. We have a simple download button here. So you can click this and download and store the results locally. So the solver we are using in the background is OpenFOAM, which is an industry standard. So the files you get are in the form of a case.foam file, and they can be read very easily by third-party software such as Paraview.
That's great. Thank you. So another question we've had come in is, do you provide training on how to use SimScale?
Sure, I can answer that as well. Yeah, so when you sign up for a professional SimScale license, it does come with some basic training. So we will have something like this, a basic screen share session, where we will walk you through a typical project that is relevant to your industry or your application. And that way you can ask any of your users to join that and learn the basics. There's also an additional option with our licensing called an onboarding project, which is basically where we walk you through your first project. So it's pretty hands-on, where we actually work with your original CAD, set up your first design and run it for you. Then what you can do is use that as a template and either use the duplicate feature that I showed you here, or just copy that project and use that as a template and go ahead with the rest of your designs. Now, if you do want to learn SimScale, we also have some great tutorials and documentation up on our website. So let me just quickly show you where you can find those. So if I go to simscale.com, we have a great learning section. So there are some tutorials and user guides that anyone can go through. And we also have some nice validation cases, as well as some articles that you can see. So the example that I showed you today was of a typical tutorial that we have here for turbo machinery flow through a water turbine. So anybody can access this, copy the project, and start to learn how to use SimScale.
That's great. Thanks, Anirudh. I think this screen that you're showing actually answers the next question. Somebody's asked if it's possible to simulate a pump as opposed to a turbine.
Yes, absolutely. So all the setup that I've showed you is, like I said, is valid for any rotating machinery. So we do have a pump example as well. As long as you can basically create a cylindrical or a conical domain around your blades, it should be pretty easy to add a rotational component to the flow. So it's not just blades. We have a lot of users, not just pumps. We have a lot of users doing industrial fans, blowers, different kinds of turbines. So as long as it's not supersonic, it should be pretty straightforward to simulate.
Great, thank you. So one other question that's come in is about the actual meshing process. What is the mesh that's used, and how do you mesh the simulation?
Sure, that's actually a good question. So you'll notice that when I did my simulation setup, I actually didn't go over the mesh, even though we have a tab for it. That is because with SimScale, we're moving towards what we call one-click simulation, where all you need to do is specify the material properties, boundary condition, and you're pretty much good to go. We've tried to automate the rest of the process, but if you do want that control and functionality over your mesh, it is there. So let me click over the mesh so that you can see it. So by default, we have an automated mesher that adds refinements anywhere it sees. So anywhere you have design features, you will see that the mesh size automatically is reduced. And same thing for inlets and outlets. So it automatically refines where it is needed. But if you do want to control or have more say in your mesh, you can do that by changing the sizing to manual. You can also add a lot of refinements yourself, whether it's on surfaces or on arbitrary bodies that you can create. We also have a mesh quality tool where you can visualize all the elements of your mesh, check the quality, and really have that control. So I would say the automated mesher works great for most cases, but that functionality for developing a custom mesh is also there.
That's great. Thanks, Anirudh. Okay, so we're out of time. Thank you very much for all of the questions that were sent in and for the attendees. So we'll see you next time. Thanks. Bye.
Thanks, guys.